So, listen, if you feel a little bit confused by this algorithm, then you're probably normal. Because it took 3 computer science geniuses to come up with the KMP algorithm. But you understand what the algorithm is trying to do. What the algorithm is trying to do is basically show you what the shift is and what the next index for comparison is. So, given a long pattern and given a long text and a pattern here, if the value here is going to be 5, that means we're going to go, the 5th character, wherever that is going to get compared against the current J character. So the slide is going to be decided by where we line up the next comparison. If the value of the next table is more than 0, 1, 2, 3, 4, 5, so if the value is more than 0, then it means that we're going to be sliding and assuming comparisons on the previous characters. So if the value of the next table is 4 in this case, then wherever the 4th character of the pattern slides, we will already know that the characters 0, 1, 2 are definitely going to match, but we don't have to check them. And that's what makes it so efficient. Okay? So that's the algorithm KMP. All right, so that's the next table. And then finally, this is the actual KMP algorithm. This is just the pre-processing algorithm to get the table, but that's really the algorithm. The rest of the stuff is very, very easy. So through this algorithm, what we're going to do is we're going to basically find the location of the location in the pattern. So therefore, we're going to use this next table to slide the pattern, because once we have the next table, now we actually have to go through the text. So this algorithm right here is basically showing you that if you have this big text and you have the pattern, it's going to show you. If you're matching here, then basically slide here, compare here. Slide here, compare here. Compare here. Compare here. Okay, that's the way it goes. And so you have these two indexes, M and N, and it ends up being there is you will repeat this until there's a match, or still more text to check. So you're going to compare it. If I is equal to M, greater than M, that means we have gone off the end of the pattern, of the text. Then the index is out of pattern. Index is location of pattern in the text, if it's greater than M. M, actually, let me revise that. M is the length of the pattern. So therefore, if we compare the pattern 0, 1, 2, 3, pattern has 4, 0, 1, 2, 3, and it's match, 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 okay? Then in that case, we want to compare the next one. But the next one is already, you've gone too far. That means you already succeeded. So quit. So if M ever goes, if we ever have a value of I greater than M, then we have succeeded. So therefore the index is the location of the pattern of the text, and the index is being computed here. If we quit this algorithm, but I is not greater than M, that means we never matched the nth character in the pattern. That means the pattern is not in the text. That's it. Okay. So that's it for that algorithm, okay? You can think about it. It's a very, very famous algorithm. I thought it would be worth, oops, that's interesting. Okay. All right, the next sequence of discussion is going to be about another string algorithm called LCS, or longest common sequence. So we're going to stick with these algorithms. Now this algorithm is important because it is example of a class of algorithms called, and I think I mentioned them before, table-driven. Right? We talk about table-driven? No? Okay. So write it down in your notes because this is important. There are two words that describe the same thing. Sometimes we call them table-driven algorithms. Sometimes we call them dynamic algorithms. It's the same thing. Table-driven or dynamic. Basically, and I'll give you a very simple idea of how it works. I actually have an example of using the Fibonacci sequence. And you can do another one. There's a few good examples that are pretty straightforward. Okay, you guys know what the Fibonacci sequence is, right? We talked about it in class earlier, right? Yes?
Yes.
Okay, remember, it was the one that started 0, 1, 1, 2, 3, 5, 8, all the time, right? So the Fibonacci sequence is where the nth element of the sequence is equal to the previous two. That's the Fibonacci sequence. So let's say you had a dynamic implementation of Fibonacci. It's not in the notes, so I'm going to do it up here. It's very, very simple. So here's the idea. You have a table, and the table will be indexed. I guess I can jot a couple things down so it'll be good reference. So the table will look something like this. So this is index 0, 1, 2, 3, let's do one more for good measure, 4. This is index 5, 6, and 7, and of course it can continue. So we know that the Fibonacci 0 is 0, and the Fibonacci of 1 is what? 1. Those are basis values. So if we're going to, so this is a table. This table is initialized with 0 and 1 in positions index 0 and 1. Okay? So listen very carefully how this works. And if you don't listen to it carefully, watch the recording very carefully. Suppose, so this table, think of this table as a data structure that's available to a function called Fibonacci. So Fibonacci can access this table. It's an array, right? And somebody says, give me the Fibonacci of 0. So this thing is going to go, by the way, here, we might put some, from a computer programming standpoint, we're going to put some what we call sentinel values or special values indicating I don't have a value for it here. Because we know that Fibonacci numbers are non-negative. So if you put a negative someplace, it means it's not a number. There's no value here. It's empty. So somebody calls the Fibonacci function and says, what is the Fibonacci of 0? So the function, the first thing the function does, it says, it indexes into here and checks that the value is not negative 1. Seeing that it's not, it returns 0. Done. Another time, somebody calls, give me Fibonacci of 1. Goes to the table and returns 1. But, and that's very nice, people only want Fibonacci 0, Fibonacci 1. Let's say somebody wants Fibonacci of 2. So if you want Fibonacci of 2, it notices that it doesn't have Fibonacci of 2. But the function knows the rule. So basically, if it's in the table, return it. Otherwise, it will assign the Fibonacci of 2, and I'll just use it as using array notation. Fibonacci of 2 will be assigned, this is the block, right? It's going to be equal to Fibonacci of 1, that's a recursive call, plus Fibonacci of 0, that's a recursive call. So the job of the function, and this is the table F. So F sub 2 is going to be assigned the recursive call F1 of 0. Now in our example, and then by the way, when it finishes doing that, it will return F of 2. The second element from the table, so F sub 2, right? So what's going to happen on this recursive call? The recursive call will call Fibonacci, which will do a lookup, and without recursing, it will return the value of 0, and this, this will return 1, and this will return, I should have really, yeah, that's good, yeah, that's good. So 1 and then 0. And so these will be recursive calls, but they'll immediately return. And so we'll return 1 and a 0, those will be added, and after they're added, they're going to be stored. This is storage, right? This is storage, and then we will return 1 to the program. Get the idea? Now, let's suppose somebody, on the next call, somebody calls up and requests the value of Fibonacci 4. Now, why is this a better example or a different example? Well, because 4 is not going to be able to satisfy 3. So what we're going to do, let's take a look at 4. So somebody requests Fibonacci 4. The first thing it's going to notice is that it's not not there. So it's going to issue a recursive call to Fibonacci of 4 will be Fibonacci of 3 plus the Fibonacci of 2. So Fibonacci of 3, it's going to look up in the table and it's going to say, I don't have that. So it's going to be, so this is going, we'll call this recursive level 0, recursion 0, and this is going to trigger recursion level 1, which means it's a call from 0 into 1, deeper level of recursion. And so what we're going to do is we're going to look at f of 3. So f of 3 is going to recursively call f of 2 plus f of 1. So recursive level 1 will trigger calls to f2, f1, but those calls will be immediately satisfied. They will just go once. These calls will not recurse. This call will not recurse either. So f2, f1 will return the value of 1 and 1, and therefore f3 will write into the table the value of 2, and it will return that value to here. This will then, so now we satisfy recursive level 1, we go to recursive level 0. We have a call to Fibonacci of 2. Fibonacci of 2 will call recursive Fibonacci of 2, but that value is hard-coded in the table. It's going to return a 1. So now recursive level 0 will simply add 2 plus 1, making 3. It will store that into table entry number 4, and it will return F4. So what just happened here? Well, what happened here is in the process of evaluating f of 4, we needed f of 3. So recursively speaking, we evaluated f of 3, but then we stored it in the table as well as returned it. So next time somebody calls f of 3, what's the complexity of that? Theta 1, lookup. How about Fibonacci of 4? Lookup. Now, what's going to happen? Now watch what's going to happen if you try to extend it. Let's say somebody says, I would like to have Fibonacci 7. So Fibonacci 7 is going to try to look up into the table. It doesn't have it. So it will have a store. Fibonacci 7 will be equal to Fibonacci 6 plus Fibonacci 5. 7 equals 6 plus 5. What's going to recurse first? 6. It's going to look at 6. Do I have table 6?
No.
Store. Fibonacci 6 is equal to Fibonacci 5 plus 4. What's going to recurse?
5.
Recursive level?
1.
2. Let's get 1 says 2. So 5. 5. Is it in the table?
No.
So I need to have Fibonacci 4 plus 3. Do I have those? Immediately loads Fibonacci 5. Fibonacci 5 returns here. 4 is a recursive call lookup, immediate. So that returns to Fibonacci of 6. Is it a 6? And therefore, the Fibonacci of 6 is stored and returned here. And then from level 0, I still need Fibonacci of 5, but that's already in the table, lookup. Okay, so tell me what is cool about this type of algorithm. Do you see why they call it dynamic? Why is it dynamic? I'll give you a clue, and you'll tell me what I'm talking about. And the clue is, it's called dynamic because when you try to get a particular value from the function, it takes different amount of work, depending upon when you call it. Why?
Your table starts off uninitialized. So
Well, it has only the initial conditions,
yeah.
because of the recursive nature of the function. And, go ahead.
So depending when you call it, you'll have to calculate previous elements in the table.
Well, we just saw Fibonacci 7. And in the process of Fibonacci 7, we filled in, yeah, because to get Fibonacci 7, we needed 6. So we went to the recursive level. 6 needed 5 and 4. We called 5. We filled in 5. We came back here. 5 and 4. We filled in 6. We returned 6. 6 and 5 is already filled in. So 7 was filled in, we returned it. What happens the next time I call for Fibonacci 7? What's the complexity of that? Okay. Now let me ask you a question. This is the kind of question I might ask you in the final exam. This is along the lines of thinking. I expect intelligent students like you to have a thought. So let's say we're talking about the Fibonacci table. What is the cost of Fibonacci of n when the table has only been initialized? Fibonacci of n. What is the cost of the n computing the n Fibonacci number? Well, don't worry about the n number. Nobody knows that. But you plug in a small value like 4. That's useful. So in order to, let's say 5. In order to compute 5, you've got to compute 4 and 3. So to get 5, you've got to get 4 and 3. In order to get 5, you need 4 and 3. So I want the Fibonacci of 5, right? I want the Fibonacci of 5. So I need 5, I need 4 and 3. I don't have 5. Do I have 4 and 3? So to get 4, I'm going to need 3 and 2. Do I have 3? No. So in order to get 3, I'm going to need 2 and 1. Do I have 2? No. So in order to get 2, I'm going to need 1 and 0. Okay, now now we've got the recursion. So we have, this is level 0. This is level 1, 2, and level 3 on the bottom. Just think about what we did here. So the call is here. The control goes here. The call goes here, and then it gets recursed here. And the call goes here, and then it gets here. How much work is being done here? Give me a theta answer. How much work is being done at level 3? Okay, let me ask you an easier question. Let's say I just call Fibonacci of 2. How much work is being done? Theta 1.
Yeah.
It's just add 2 numbers. Okay, so we do a theta of 1 unit of work here to compute this. And that unit of work really we can count here. How much is being done at level 2? Another unit of work, because we got to do an addition. Once we have that addition, then this is already computed. How much work is being done here on this level, level 1? Another theta of 1. 4 is computed. How much work is being done here then? Another addition, theta 1. How much work to get theta 3? It's already done. That's also theta 1. So when I do when I do Fibonacci of 5, how many units of work did I do, roughly speaking? N minus 1, but if I generalize it to n, I would call it theta n. Okay, does that make sense? So if I call it theta n, the amount of work being done is n. Now the question is that really a great algorithm? The answer is, yeah, it's a great algorithm because if you want to see Fibonacci of 5, if you were to write the recursive function Fibonacci of 5, would trigger Fibonacci of 4, followed by Fibonacci of 3. This was Fibonacci of 3, Fibonacci of 2, Fibonacci of 2, Fibonacci of 1, Fibonacci of 1, Fibonacci of 0, Fibonacci of, that's the base case. This is going to be Fibonacci of 1, Fibonacci of 0. This is going to be Fibonacci of 2, Fibonacci of 1. This is going to be Fibonacci of 1, Fibonacci of 0, and this is going to be a base case. If you wrote this as a recursion, you would execute every single bit of every single branch. You would get a theta of 1 for every single node. You got me so far? So, if somebody wanted to compute not Fibonacci of not Fibonacci of 5, but Fibonacci of 6, then you would need to basically do all of 5, and then you'd need Fibonacci of 4, which essentially will be, all of this would be recomputed again. So, looking at this picture, tell me what do you think is the complexity level of Fibonacci implemented recursively? Classify it as some kind of a mathematical type of function. Don't get too technical. Just describe the function. What kind of function is this? What type of complexity is this? Don't solve it. You're not going to solve it right now. We don't care about solving it. Anybody? Too detailed. Just describe it. Starts with EXP. Yes, it's exponential complexity. It is exponential complexity. So Fibonacci recursively coded is exponential. And exponential is notoriously known as an extremely non-feasible algorithm for large values. For large values, we cannot do anything exponentially. But from my question on this dynamic implementation, we see that our dynamic implementation actually is what? Linear in the what case?
Initial case.
Yes, but classified as an algorithm. We have best average, and worst.
Worst average.
Worst case, and the worst case is the initial case. So the worst case is the table is essentially empty. We have to fill in the whole table. What's the best case of this? Constant time. Best case constant time. Because basically, once I call Fibonacci of 7, the table gets filled in. Notice that what happens in this table is if you want to trace how much work I'm saving. Now, basically, so if you want to do this, so let's count how many branches are here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Can't count. Under 4. 1, 2, 8. So what I'm going to say is basically it's going to be 8 more branches, right? You understand what that 8 means? That means I'm lazy. Okay, so it's going to be 8. So if I were to execute this algorithm recursively, I would have to pay unity cost for every single node. So we can count them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 23. So there will be about 23 units of cost. And of course, if I were to do this way, let's see what the cost would actually be. So I'm calling, so I definitely have to do addition here. You know what I'm saying? Addition is the cost, really. Addition is the cost. So I would have to do addition there. F6 would lead me to what? F5. I would have to do addition there. Where's F5 going to lead me to? F4, F3, F2. I have to do an addition, but I'm done here. So therefore, what's this? This is going to be 1 unit of cost. What's this going to be? This is going to compute F2 plus F1. This is already done. This is in the table, so it's going to be 1 unit of cost. 1 addition. When I come back up here, notice that this is already in the table. 1. 1. 1. Okay, so what's our complexity? Well, notice there are 5 circles here. So therefore, it will generalize to n minus 1 circles. So therefore, you can see it's a linear complexity. But now, 5 circles, right? 1, 2, 3, 4, 5. But now, Fibonacci of 6 is not Fibonacci of 5. I have to now execute Fibonacci of 4. But that's already in the table. So therefore, this is a unit of work. Just look up. That's it. I'm done. Everything else is never done again. That's the initial call, worst case complexity, of calling Fibonacci of 6. If subsequently I called Fibonacci of 7, I would need 1 unit of work here, and then this would be just a lookup, which would be f of 5, right? So how much work would I be doing? 1 or 2 units of work, which is, if you do 1 or 2 units of work, that's just constant time. And next time if I do f of 8, 7 is already in the table, 6 is in the table. Okay, you understand? Dynamic, which means that our knowledge base about the solutions is growing dynamically. So the complexity of returning values is changing dynamically. It's not the same. Once you pay the big price, you never pay it again. If you compute Fibonacci of 10, Fibonacci of 7 is free. Get the idea? And our computation of Fibonacci, our Fibonacci function has a linear cost because of this information that we're saving. Now, are there different ways to implement Fibonacci? Well, of course there are. You can just start in an array with 0 and 1, and just keep looping, adding the previous 2, previous 2, previous 2. You just load up the information. But how far do you go? How do you know what Fibonacci you're going to need? Maybe you know. Maybe you don't. I'm just saying that this is this is the idea of dynamic algorithm. So, let me tell you one more thing about dynamic algorithms. Dynamic algorithms are called table-driven. The reason they're called table-driven because the implementation of the dynamic behavior is done using table storage. And tables can be one-dimensional, like in this case. Tables could be two-dimensional, like a matrix, or tables could be multi-dimensional, like, for example, an array of matrices. So they could have height, columns, rows, and depths, and more complicated things. So tables can be 1, 2, 3, 4, or n-dimensional. Okay? What makes all these algorithms kind of the same is that there is an ordering or a dependency, which I can exemplify very simply like this. So let's say we extend this table, okay, and we say, for example, this is the ith Fibonacci number. What I know is that the dependency here is that the ith Fibonacci number depends on the I minus first and the I minus second. So therefore, if I have these already filled in, then this doesn't need any more processing around. So this is called topological ordering. When you can show that a particular element in a vector is dependent on other elements. In this case, the ith element depends on I minus 1, I minus second element. In this example that I'm going to show you next, you're going to find out that the topological ordering is going to be two-dimensional. And so it'll become a little bit more interesting relationship. But the cool thing about it is this. If you can find a topological ordering in a one-dimensional array, then the complexity of your algorithm will never be more than linear. Think about it. Notice my complexity. That means to fill in this element, I only need two operations, the addition of this and this. So I need to get this and I need to get this. So therefore, in order to fill this in, I only need theta 1 to fill this in. I only need theta, once this is done, I only need theta 1. Look up, add. Theta 1. Look up, add. Theta 1, theta 1. So the topological ordering makes it so that you can grow this dynamic table in a linear cost. Okay? Now, if your topological ordering is two-dimensional, so you have a matrix, and I don't care how that matrix is built, but all I can tell you, there's a topological ordering. So let's say I have a cell here. Now these are all cells. But let's say there's a dependency here, and a dependency here, and a dependency here. Let's say those are, so what I'm showing you here is that the cell that's highlighted depends on three other cells. Well, if I build it carefully, it looks like I only require 3 operations for each cell. So therefore, the complexity of any algorithm that is driven by this table is going to be bound by theta 1 times the number of cells. Because 3 is 1 in theta notation. What I'm telling you is that every cell needs 3. Well, if every cell needs 3, it's like 3 operations we just lump together as theta 1. The relationship between any cell is the same. So it's constant. It's not like this one needs 3, but this one may need all of them. And how big is this table? I don't know. If you have the same number of rows and columns, you could have n by n, it could be n squared. So therefore, the complexity of this algorithm would be the number of cells times theta 1. And in this case, it will be n squared. If it's not n, but m by, let's say, m, then the complexity will be nm, theta nm, times theta 1, well, theta nm. Okay? Make sense? So if every piece of information can be gleaned from this table, and this table has mn entries which have a topological ordering that looks like this, or perhaps like this, then nm is the theta of that complexity. For any one of these. I can fill in this table with the nm operations. Okay. So let's take a look how that can happen. And now that you have the background of Fibonacci, this should be a little bit more straightforward. What we're going to try to do is we're going to try to find the longest common sequence. And let me explain to you what the heck that means. Oh.